Hi everybody. This video is an introduction to section 16.4 on Green's theorem. So Green's theorem gives a relationship between a line integral around a simple closed curve C and a double integral over the plane region D bounded by C. And so when we say D here, D represents all points that are inside and on that boundary curve C. Okay, before we go further, notice I have this phrase, simple closed curve, to describe C. And so I want to make sure that we understand that terminology. So we say that a curve is simple if it does not cross over itself. So the two curves that you see on the left are simple. The two curves that you see on the right are not simple because they cross themselves at some point. We say that a curve is closed if it starts and stops at the same point. So the two curves on top are not closed. The two curves on the bottom are closed. And so when we talk about the curves C that we're interested in, we want them to be simple and closed. So we want them to start where they stop, and we want them to not cross over themselves anywhere. Great. One more definition. A curve is said to be positively oriented if the region D is on the left. So in other words, if the curve goes counterclockwise. So A here that you see here on the left is a region with positive orientation because the region D is to the left of the curve C. If you were to walk along the curve C in the direction of the arrows, D would be on your left. B on the right here has a negative orientation because if you walked along C in the direction of the arrows, D would be on the right. All right, so here we go. Here's what Green's theorem says. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous partial derivatives on an open region containing D, then the line integral around C of P dx plus Q dy is equal to the double integral over D of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y. Great. A note on notation. Because C is a closed curve, you'll sometimes see a circle around our integral. That's just letting us know that C is a closed curve, that it starts where it stops. And because C is the boundary of the region D, you'll sometimes see the integral written over boundary of D instead of C. I'd also like to note that Green's theorem is the fundamental theorem of calculus for double integrals, and let's see why that's true. So here's our old Calc 1 fundamental theorem of calculus, and let's compare that to Green's theorem. So in our old fundamental theorem from Calc 1, note that we integrate a derivative, and the result is the original function on the boundary of the interval a to b. With Green's theorem, again, we're integrating derivatives, and the result is the original functions on the boundary. Great. So let's see Green's theorem in action in a couple of examples. Let's first evaluate the line integral of xy dx plus x squared y, where C is a triangle with vertices 0, 0, 1, 0, and 0, 2. And let's start with a visualization of C. So we have a triangle with vertices at 0, 0, 1, 0, and 0, 2. It'll be helpful momentarily to find the equation of the line connecting 1, 0, and 0, 2. And that's the line y equals negative 2x plus 2. Here's the scratch work for that if you're curious. Now, we could compute this line integral as it's been given to us, but since the triangle is made up of 3 separate line segments. In order to compute the line integral, it would require us to do 3 separate integrals. They would not be difficult, but it's a little bit tedious, so we're going to use Green's theorem instead. Note that the p of xy is x times y, and our q of xy is x squared times y. So then, according to Green's theorem, the line integral of xy dx plus x squared y dy is equal to the double integral over that triangle of the partial derivative of q with respect to x minus the partial derivative of p with respect to y. And we're going to describe this triangle by letting x run between the numbers 0 and 1, and y run between the value 0 and that line minus 2x plus 2. All right, let's go to a new slide so we have a little more room to work. So here is our double integral. Notice that the partial derivative of q with respect to x is 2xy minus the partial derivative of p with respect to y, which is x. We integrate first with respect to y, so that gives us xy squared minus xy, which we evaluate for y between 0 and minus 2x plus 2. So we plug in that minus 2x plus 2 for y and get x times minus 2x plus 2 squared minus x times minus 2x plus 2. Let's go to a new slide again so we have more room. Here's where we were. Now, I'm not going to do anything interesting except just multiply everything out and collect like terms. So that leaves us with the integral from 0 to 1 of 4x cubed minus 6x squared plus 2x. We integrate with respect to x to get x to the 4th minus 2x cubed plus x squared, and evaluate from 0 to 1 to get a final answer of 0. Great. So for the line integral here, instead of having to do 3 separate integrals to get those 3 line segments around the boundary of our triangle, we instead did the double integral around that triangular region. Let's do one more example. Let's evaluate the line integral of x e to the minus 2x dx plus x squared plus 2xy dy, where c is of the circle x squared plus y squared equals 4. So let's start with the visualization of c. So it's this circle that we see here, x squared plus y squared equals 4. So a circle centered at the origin of radius 2. And we could compute this line integral using the parametrization x equals 2 cosine t, y equals 2 sine t. But if you write that out, it leads to a really unpleasant integral. You can do it. There's a u substitution and integration by parts. It's definitely a doable integral, but not a pleasant one. So instead, let's use Green's theorem. Note here that our p is x e to the minus 2x and q is x squared plus 2xy. And so Green's theorem then tells us that the line integral we've been given is equal to the double integral over that entire circle of our partial derivative of q with respect to x minus p with respect to y. Now, the partial derivative of q with respect to x is 2x plus 2y, and the partial derivative of p with respect to y is 0. So we have the double integral over d of 2x plus 2y. Since D is a circle, we're going to describe it using polar coordinates. So we're going to switch everything into polar coordinates. We're going to let R range between 0 and 2 and theta range between 0 and 2 pi. And so our double integral will have as our bounds theta from 0 to 2 pi and R to 2. We'll replace the 2x with a 2r cosine theta and the 2y with the 2r sine theta. Since it's a polar integral, we always have to include that additional r, dr d theta. Great. So we're going to put the r's together. So I'll pull out, so we have a 2r squared. We integrate that with respect to r to give us 2/3 r cubed times cosine theta plus sine theta, evaluated for r from 0 to 2. That gives us 16/3 times the integral from 0 to 2 pi of cosine theta plus sine theta. Integrating with respect to theta, we get 16/3 times sine theta minus cosine theta, and evaluate theta from 0 to 2 pi to see that we get an answer of 0. Great. So this is all for our introduction into Green's theorem. We'll do a lot more examples in class. Thanks so much. See you then.